Hello. So this is a joint event of BRACIS 2020, the premier conference in AI in Brazil, and the Center for Artificial Intelligence, the new sorry, I got some sound interference here and got distracted. So this is a joint, as I said, joint conference of BRACIS 2020 and the Center for AI, which is this new center that has been started with IBM and the University of São Paulo and FAPESP. We decided to jointly have this live to reach the community and to straighten our ties between the AI community and the new center. Thank you for all the organizers of BRACIS for agreeing and helping us in putting this together. And without further ado, I'd like to introduce David Cox. It's a great pleasure to have you here. We have a very good audience. David Cox is the IBM Director of the MIT-IBM Watson AI Lab, this huge cooperation between MIT and IBM that's pushing the boundaries of AI with really interesting research. We'll learn some of that today. Before joining the lab, Professor Cox was at Harvard University, which shows how eclectic he is. He can go from MIT and Harvard, but he was at the Department of Molecular and Cellular Biology and the Center for Brain Science. He also was one of the first people who put together a massive online course. He had his course on fundamentals neuroscience that was watched by more than 750,000 people. So I think with all that, I mean, I don't want to talk anything more, so I can leave the most of the time to David, and so he can join the most of it. If you want to have questions, we collect questions from the website, from the chat in the website, the underline feed. I will put together those questions and I'll bring them to David at the end. Thank you.
Great, fantastic. Thanks for having me here. Can you hear me okay?
Yes.
Okay, great. And hopefully you can now see my slides as well. Are you able to see my slides?
Yes.
Okay, fantastic. Thanks so much. So thanks so much for inviting me to come here. Apologies for speaking in English, and please your questions in English as well. I'm really excited to tell you about work we're doing at the MIT-IBM Watson AI Lab based in Cambridge, Massachusetts. This is, as Claudio mentioned, this is a first of its kind collaboration, a very deep collaboration between MIT and IBM research. And today I'm going to tell you about one of the major focuses of our lab, which is Neuro-Symbolic AI. And before I get into what that is, I just want to take a moment to talk about this term, artificial intelligence. Because as Claudio mentioned, I'm a recovering academic. I used to be a professor at Harvard. I was a professor for 10 years before I joined IBM about 3 years ago. And like many of you, I'm sure, who are practitioners and who study artificial intelligence, I would say 2018 and before, we were all very, academics were very uncomfortable with this term, artificial intelligence. You know, we would try pretty hard not to say artificial intelligence. We'd say machine learning, or we would, you know, be more specific, say deep learning. And for whatever reason, 2019 and forward, you know, everybody now we've all given up, and we're all calling this now artificial intelligence. We're all using this term. You know, we're doing it, Google's doing it, academics are doing it. It's just some shift happened. But when I joined IBM, they had done something that I really appreciated, which is to frame what kind of AI we're talking about when we're talking about different kinds of AI. And it's very simple. They simply put an adjective before. And this is something that was done in something called the Global Technology Outlook, which is an exercise that IBM Research does for the IBM Corporation once a year, where we envision what the future will hold. And in 2018, the focus was on AI, and basically broke AI down into 3 different kinds of AI, starting with narrow AI, which is where we are today. And that's not to say it's not powerful, not to say it's not disruptive, but to say it's fundamentally limited in important ways, which I'll get into in a minute. And also to bookend off general AI, the sort of general intelligence, that sometimes comes up in science fiction, and then really to put in the middle. This is really where the stakes are, and this is what the lab I run is about. Broad AI. How do you make AI that's broadly applicable to all the problems that we want to solve? And just to sort of dial down one step deeper, the reason we say that today's AI is narrow is because it's fundamentally single task, single domain, one thing well. You train with deep learning in particular, you can take huge amounts of labeled data and you can train a system, and that system can perform potentially better than humans and faster than humans, but you need to have enormous amounts of very carefully curated data. And we have a picture here of a skin lesion, because this is kind of a canonical example. If you imagine having thousands to millions of examples of skin lesions, and you have doctors rate them as being cancer or no cancer, you could train a system that's been trained with the equivalent of practicing medicine for hundreds of years. So it's not a great surprise that you could potentially do better than humans, but it's only going to do that one thing, and it requires an enormous amount of data to make it work. Meanwhile, on the other end of the spectrum, this is sometimes what the public likes to talk about, and philosophers and the press sometimes focuses on or perseverates on this idea of general AI, cross-domain learning and reasoning, broadly autonomous. It decides what it wants to do on its own. This is the thing that Elon Musk compared to summoning the demon, which is always fun when you work in AI and someone describes your work as summoning the demon. Or Stephen Hawking warned that artificial intelligence could end mankind. These are very dramatic statements that people are making, and the fact of the matter is we're nowhere close to having any of these problems actually be apparent, and that's simply because we're at the very beginning and cusp of AI. So I would argue we don't really need to worry about these things, but rather what we need to focus on is this opportunity, which is in between, and that's what we call broad AI. And that's AI that's multitask, multi-domain, can do more than one thing, can take knowledge from one place and apply it to another. It's multimodal. It's not just images or not just text, but images and video and audio and structured data and unstructured data all brought together. It's distributed, needs to run in the cloud and on our edge devices, and perhaps even in sensors. And then importantly, it's also explainable. So one of the barriers to adoption of AI, and to first approximation, these are all barriers that we need to break down to the adoption of AI. Humans need to use AI, and to use AI confidently, they need to be able to understand it. So we need systems that are able to be understood by humans, to meet humans halfway, so they can be used as a tool. So the premise here is that we're not really aiming to build generally intelligent systems that are going to go off and decide what they want to do on their own, but rather we'd like to unlock the power of AI for a broad range of applications. That's really the stakes. And this is kind of a little bit of a roadmap for IBM Research and for particular of where we think the stakes are. So looking at how do we build more explainable AI systems. Many deep learning systems, which are very powerful, are basically black boxes, and they're hard to understand. Systems need to be secure. There's a whole weird new world of AI security that's evolving, and we need to close those security gaps to be able to confidently deploy AI. The systems need to be ethical and fair, and in many cases this is for the good of society, but it's also in many regulated industries. This is simply part of doing business. If a bank is required in many cases by regulators to show that their algorithms are fair. If you deny a loan, you need to be able to demonstrate that your system was fair in denying that loan. And then at a practical level, we also need to be able to learn from more from small data. So I mentioned that many of our AI methods today require huge amounts of labeled data to work. But in many applications at enterprise, and many hard problems that we'd like to solve, we'd like to benefit from AI, we don't actually have huge amounts of data. Or in cases where we even do have huge amounts of data, it's rare to have huge amounts of carefully labeled data. So we think it's important to learn from small data. As much as people talk about big data, small data is important as well. So some of that has to do with transfer learning, so how to learn to take what you know from one domain and apply it in another. But increasingly, and this will be the topic of the rest of my talk, learning how to extract the structure of the world and then flexibly reason about it. I'll talk a little bit about what that word reason might mean in this context. And then finally, just to round out the sort of issues with broad AI, we also have a problem with the power consumption of AI. So by some estimates, year over year, our energy consumption for computing is increasing at such a rate that by the year 2040, we're estimated to exceed the power budget of the planet Earth. Simply with computing. So that's to say that there's not enough solar radiation hitting the surface of the sun, Earth from the sun, and there's not enough stuff we can dig up out of the Earth and burn to keep up with our computing habit. And AI is one of the most energy-intensive workloads we have. So thinking about how to drastically lower power AI using technologies like analog computing is an important part as well of what we do in the lab. But I want to go back to this this slide for a moment to really ask the question, so what exactly is it that's narrow? Why am I saying that today's AI toolbox is accurately described as being narrow AI? Well, first of all, let me sing the praises of today's AI for a moment, because AI can do some pretty amazing things, and that's been largely driven by the successes of a technology called deep learning, which I'm sure all of you have know quite a bit about. And of course, in 2015, the writing was already on the wall. Forbes announced that deep learning was going to eat the world, and I think to a first approximation, deep learning has upended a lot of the domains where we work and done some pretty amazing things. So here's an example of a result. From the literature that I found very impressive. So when I was a professor working in AI and computer vision in particular, when I started out, it wasn't clear to me that that this was something that we'd be able to do. So this is a system that can take a photograph and it can actually generate a natural language caption of that photograph. So you put in the photo on the left, and it comes back with a man in a black shirt is playing a guitar. Or you put the image in the right, and it comes back with a caption, construction worker in an orange safety vest is working on the road. Now, these are things that we increasingly take for granted, but I have to say, just put yourself back a few years. In 2012, this was a radical new capability. So, this was enabled by deep learning. This wouldn't have been possible without it, and it's really impressive. At the same time, there basically aren't very many games left that humans are better than machines at. Start with everything from Jeopardy, which the original IBM Watson system beat in 2011, to the ancient game of Go, which Google DeepMind's AlphaGo system was able to beat the world champion in. We even have systems that will beat the world champion in poker. A group of Carnegie Mellon built that system. And IBM's even created a system, for instance, that can carry on a lucid debate with an expert debater. So, if you like computer systems that can argue with you, we've got you covered. And even things like art, that we would have thought would have been the sole province of humans, increasingly we're finding AI systems that can create. So everything from style transfer, where you take a photograph and then you can re-render it in the style of any artist you like using deep learning methods, to systems like BigGAN. So this is a generative adversarial network on the right, where each of these images, even though they look like a dog and a bubble and a cup of coffee, these aren't actually real objects in the world. These are the figments of the imagination of a generative adversarial network. So you just put in a random number and it generates this beautiful high resolution image. So truly stunning things that we've been able to do with deep learning. But there's a problem. So if we take an image like this, unusual image, and you ask a deep learning system, a state-of-the-art deep learning system, what is this image? You'll get an answer like this: teddy bear. And I would submit that this is one of the least teddy bear-like images possible. Basically, this is not a teddy bear at all. But you can, and in fact, this is a piece of modern art. It's a piece of work called Luncheon in Fur by Merritt Oppenheim. It's in the New York Museum of Modern Art. But you can kind of start to see what went wrong here. Why did it decide this was a teddy bear? Well, it's roughly round and it's got fur, and the things that were in the training set, that were round and had fur, were much more likely to be teddy bears than to be this particular unusual fur-covered saucer cup and spoon. And it's actually worse than that. So even completely valid normal images, if you just take objects, this is an example of a state-of-the-art object detection system called Faster RCNN. If you put objects in contexts where they don't belong, even though the systems perform quite well in normal contexts, they actually completely fall apart when you have unusual context. So like, if you take this monkey and you put a guitar in front of him, rather than seeing a monkey with a guitar, all of a sudden now it thinks the monkey is a person, because monkeys don't usually appear next to guitars, and it thinks that the guitar is a bird. And the reason you can kind of imagine why that is because the coloring of the guitar in this jungle environment is much more commonly a tropical bird than it is the guitar. So as amazing as deep learning systems are, they fail, and they fail in really interesting ways. And even if we go back to this amazing captioning system that I brought up at the beginning of the talk, we find that if you take that same system and you apply images that are just a little bit unusual to it, you'll get things like this. So this is captioned as a man riding a motorcycle on a beach. This one's captioned as an airplane parked at the tarmac on an airport. And this one is a group of people standing on top of a beach, which is actually technically correct, but I would suggest that this kind of misses the point. So there's a sense in which deep learning systems, even though they can do these kind of amazing tricks, in a very deep sense, don't really understand the images that they're presented with. They don't really understand the inputs that they're working with. And this is a problem if we need to confidently deploy these systems in the real world. It actually gets worse. So most of those images, as I mentioned before, and as many of you surely know, these systems require huge amounts of data to train. And there's a data set called Imagenet, which is millions of carefully curated images. And these are what are used to train these data sets. But in contrast, we don't actually need millions of images as humans to recognize objects. In fact, we can recognize objects from a single image. So this is just in stark contrast to how the AI systems are working. So even if you haven't seen this object before, and usually when I present this live, audiences, only a few people have ever seen this object before, you can still answer questions like, is it present in this image? And I think we'd all agree it is. Or how many are present in this image? And I think in this case, we'd all agree that there are 2 of that object. Or is it present in this image? And I think we'd all agree, yeah, the object is there, but it's weird. So we're able to not only recognize the object from a single example, but we're able to reason about it in unusual contexts and different settings that are mixtures of objects with objects we've seen before. So this is a really amazing ability that's very different than what our current deep learning systems are able to do. And it's even worse than that. So if you look at Imagenet, this data set that really enabled deep learning and particularly computer vision, and you look at the category, has many categories of objects, including one like this one, chair. These are some examples from the chair category. And if you look, one thing that you'll notice is that every one of these images has a chair, and that's fine, that's what it's for, but they're all in a sort of centered canonical view. So, or, in the case of the middle one, like there's lots and lots of chairs. But it turns out that, like in the real world, objects don't always appear perfectly centered. We created a data set actually to illustrate a problem here called Objectnet. So this was a collaboration in the MIT-IBM Watson AI Lab between Boris Katz and Andre Perbu at MIT and Dan Gutfreund in my group at IBM, where they asked mechanical Turkers, people around the world, they downloaded an app, and their job was they got instructions that said things like, take a chair, put it in your living room, and put it in this orientation so it fits in this bounding box. Or take a hammer, take it into your bedroom, put it on the bed, and fit it into this box, snap a picture, and send it. And they collected this data set called Objectnet, which includes a subset of the categories of Imagenet. But the objects are just in slightly unusual settings and slightly unusual views. Now, all of these objects are still perfectly identifiable by us. And this is an example of how this would work. So the person would get an image, they get a prompt to take a picture of the object in that position, a knife in the bathroom or a nail polish bottle on a chair. We as humans don't have any trouble recognizing these objects. But it turns out that these Imagenet trained models, these deep learning models, which perform fabulously well on images when they're perfectly centered, as they are in the Imagenet data set, perform above 90%. Sometimes people will say that they're actually performing better than human subjects. It turns out if you just take those objects and put them a little bit out of context and in slightly unusual views, the performance drops by 40 to 45%. So they're just utterly destroyed by simply putting a hammer on a bed, and suddenly the system completely fails. So this is highlighting an incredibly serious problem in these systems. Imagine deploying actual robots in the environment that have to recognize objects, and they fail completely if the object isn't in a canonical pose in a canonical environment. It's just a catastrophic failure. So these are gaps we have to close. The other thing that you likely have heard of, which is a weakness of deep learning systems, is that they're vulnerable to hacking. So this is an example from Pinyu Chen at IBM, where he took, again, the same kind of captioning system I highlighted earlier, where you take an image and it produces a caption. And here on the top, we have an unaltered image. So take the stop sign picture, the system produces beautiful captions like a red stop sign sitting on the side of the road, or a stop sign on the corner of the street. These are good captions, they're correct. But what Pinyu did is he very carefully perturbed the image, changed a few pixels here and there in a way that's below the threshold of our ability to perceive it. And you can actually trick the neural network into classifying, creating any caption you like. In this case, a brown teddy bear laying on top of the bed. So those two images look the same to me, top and bottom, but to the deep neural network, it's confidently declaring that bottom one is a teddy bear. And this is a huge vulnerability for computer vision systems. And this is something that clearly our visual system, our brains don't have this problem, but deep learning systems do, and we need to fix this. And actually, we do some work on this area as well at the MIT-IBM Lab, and we created this fun thing, a few folks in my lab, where imagine you have a person detector. So this is an AI system that can accurately put a bounding box in purple around a person. You can imagine in a surveillance context, you might want to know if somebody's intruding in your facility so you can track them. What Sija and Chuanfu, who are the two gentlemen there, did was they created a pattern on a shirt that, even in spite of irrespective of its wrinkling and its orientation and its lighting and how far close it is, will basically make you invisible to a deep learning based person detector. So while it's able to detect Sija on the right, as a person, Chuanfu, who's standing next to him, is wearing this shirt, which is this kind of crazy loud shirt, but it's basically like AI camouflage. You wear this shirt and you're invisible, and this works even if you move around. It works even if there's different curvature and things like that, different lighting. So these are huge problems. Like, we do a fair bit of work where we invent new kinds of attacks against these classifiers, new kinds of hacks, because ultimately what we want to do is we want to understand them so we can guard against them. But it's safe to say that today in deployed AI systems, we don't have good defenses against these different kinds of attacks. But even going beyond that, and this is getting to the topic of the title of the talk, Neuro-Symbolic AI, there are kinds of problems that deep neural networks fail at, even when you give them best case scenario, as much data as you like. It's just challenging to train the neural network to do the right thing. So for instance, if we have question answering problems, like if I take the image on the left and I ask how many blocks are on the right of the 3-level tower, this is something that even a child can reason about and answer and look at the picture. But it turns out that AI systems really struggle. It's hard to train a neural network that can actually solve this. Or intuitive physics questions like, will the block tower fall if the top block is removed? Or are there more trees than animals? Or what is the shape of the object closest to the large cylinder? And these are slides I got from Josh Tenenbaum, who's one of our collaborators. And this last one is actually a data set called Clever, which was designed by some folks at Facebook plus Fei-Fei Li at Stanford to sort of illustrate a problem with deep neural networks. So these are just rendered objects, and they have different properties, different colors, different shapes, different materials, and you just have to answer simple questions about them. And it turns out that this is something that's very hard for deep learning systems to do and to be trained to do in a traditional way. So there's a problem. And the real goal here then is to figure out how do we solve it. And actually, so to find the solution, we're at the MIT-IBM Lab, we're going back to the beginning of AI. So as it turns out, if you didn't know, the term artificial intelligence was actually coined in 1956, way back in 1956. At a workshop that was co-organized by IBMers like Nathaniel Rochester. You can see who the IBMers are because they're the gentlemen wearing ties. And then future MIT professors, as it turns out. So IBM and MIT have been together for a long time. People like John McCarthy, Claude Shannon, Marvin Minsky. Way back in 1956, dreamt of the future that we'd be here today talking about artificial intelligence. And neural networks were absolutely around at the beginning. So there was a notion of artificial neurons and perceptrons, ultimately turned into artificial neural networks and were rebranded as deep learning. But there was actually another kind of AI that's been around since the beginning as well, which is called symbolic AI. And the interesting thing about neural networks is, deep learning is basically a rebrand of neural networks. And as many of you know, there was no invention or huge conceptual advance that suddenly made neural networks work. What made neural networks work was the availability of enough data to train them. And remember, these are incredibly data-hungry systems, and also the compute to run them on. They're also very compute-intensive. So in a sense, deep learning was waiting for decades for the right compute and the right data to come along. Now, symbolic AI has not enjoyed a resurgence the same way that deep learning has. It's not yet kind of come back to the fore and gotten that excitement around it. But one of the central theses that we're pursuing at IBM, and also at the MIT-IBM Lab in particular, is this idea that symbolic AI has also been waiting, but it's not waiting for more compute or more data, but rather it's waiting for neural networks. So in many ways, neural networks working now allows us to combine them with symbolic AI methods in a way that each of these methods can complement each other's strengths and weaknesses. And that's really the spirit of Neurosymbolic AI, which is what I'm going to tell you about next. So what is a neural network? What is deep learning? Well, fundamentally, it's a nonlinear function approximator. So we take what we have, say images, and we map it to what we want. In this case, labels, like a one hot coded vector that tells you what the object is. And we train it with lots and lots of pairs of what we have and what we want, what we have, what we want. And the internals of this actually are a bit of a sheep in wolf's clothing. It looks complicated, but it's actually not. The forward pass through this is all basic linear algebra. The training method is basically calculus. It's not much more than the chain rule back propagation. But the key is that you train many millions of parameters based on lots and lots and lots of data, and you get a system that maps from one to the other. So this is very powerful. This works amazingly well, and it's really ignited a new renaissance in AI. But there's another way of looking at that apple. And in the context of symbolic AI, an apple might look more like this. We know things about the apple. We know that the apple has an origin. It comes from an apple tree. We know that an apple is made up of parts. It has a body and a stem. We know the body has properties. It's round. It's got the size. If it's in your hand, it's got color. It could be red or it could be green. We know that an apple is a kind of fruit. We know it comes from, we know something about the evolutionary history even of apples and how it's related to other plants. We have all that knowledge. And I would argue when we recognize an apple, or we need to decide what happens, reason about what's going to happen with an apple, we can bring all of this knowledge to bear. And that's a very different way of looking at things than having a system that maps from what you have to what you need. And the question then is, can we take some of these ideas and put them together and build something that's more than the sum of its parts? So this is a collaboration that we've been doing, for a while now, together with Josh Tenenbaum, who's a professor at MIT, thought leader in this area, just won the MacArthur Genius Award this year, together with his student, Jiajun Wu, who was a student at MIT. Now he's an assistant professor at Stanford, and together with Chuang Gan, who's a researcher in my group and IBM research at the MIT-IBM Lab. So the idea here is kind of, can we have a best of breed combination of neural networks and symbolic AI? And in particular, we're going to tackle this problem of question answering and using this clever data set as an example. This is kind of a hello world for neurosymbolic AI. So it's not a real world problem, but it's interesting in that traditional neural networks struggle to solve it. And we can sort of ask, can we get further down the road using combinations of neural networks and symbolic AI? And so typically the way this test works is you're given an image, and then you're given a question. The question's in natural language, in English in this case, and then you just have to answer the question in natural language. So what is the shape of the red object? So now traditionally, if you kind of follow the ethos of deep learning and how you're supposed to solve this problem, you would follow a paradigm that we would call end-to-end training, which is basically map from what you have to what you need, and try not to get in the way in the middle. Like just do it end to end, and then there's some questions about what the architecture of the neural network is, but basically stay out of the way. So you would take your image and your question, you input those into your neural network, and then you'd map that to the answer. So this basically then those two things go in, and you try and get the answer sphere out. Now, there's a lot of things going on here. So there's concepts like colors and shapes, and then there's reasoning, like things like counting or identifying the property of a particular object. And the thing that's frustrating about this end-to-end approach is that these things end up being fundamentally entangled in the neural network. So there's nothing forcing the neural network to not keep these things separate. So they can be all mixed together, and that's problematic for a number of reasons. But one of the key reasons is it's really hard to transfer, based on those concepts to a new task, because the tasks, the concepts and the reasoning and the operations you're performing are all mixed up. So hard to transfer this to image captioning. You basically have to retrain the whole system or instance retrieval or whatever. So we wanted to step back and say, okay, well, how do we solve this task? We don't really have problems transferring what we know about objects from one context to another. How do we solve it? Well, so the first thing we do is, if you kind of introspect, how would I answer the question, are there an equal number of large things and metal spheres? First thing is you use your visual system, you read the question, see if there's something about large things, and then you use your visual system to find the large things. You look around the image, you find the large things. Okay, fine. That's the kind of thing you're using visual perception. There's another part of the question that asks about metal spheres. Okay, I can use my visual system to filter and find the visuals, the metal spheres. And then critically, then you do an operation, a logical operation, a symbolic operation, where you compare those two numbers. And you say, okay, there's three of those, there's three of those. Okay, the answer is yes, they're equal. Now, if we unpack that, there's a part that's clearly visual perception, and that's the kind of thing that we know that neural networks are good at. I mean, they're good at processing all the correlated pixels of images. It's a part about question understanding, and we know that neural networks, particularly RNNs and transformers and things like that, are good at processing natural language and all the sort of correlations and vagaries of natural language. But then there's a piece that's really very clearly not those things, and that's a logical reasoning piece. We apply some operations like counting and comparison to those problems. So then the question then is, well, can we build a system that actually keeps those parts separate? Use neural networks for what they're good at, and use symbolic methods for things that symbolic methods are good at. And this is a complicated figure. This is the system that the team produced in 2018. This was a paper in NeurIPS. So it was an oral spotlight. So this is a top paper in a top conference. And basically, just to unpack this, there's a part that's vision, and for that vision part, use a convolutional neural network, which is kind of the sensible thing to do to take the image. But rather than trying to answer the question the whole in one shot, you take the CNN and use it to basically turn the image into a structured representation. So they sort of de-render the object, take the scene, and then turn it, figure out what all the components are and what their properties are, what color, what shape, what material, what location. And then we're going to take the question and we're going to put it into a language model, in this case, a recurrent neural network like a BiLSTM, which is, we know are good at processing language. But rather than trying to go end to end, or rather than trying to label that question or to translate that question into another language, so something we can do with a sequence-to-sequence model, for instance, with one of these models. What we're going to do instead is we're going to translate it from a question into a symbolic program. So you take the question, you turn it actually into a series of operations that we can execute, and then we're going to execute that symbolic program on the structured representation. So everything on the right side of this image is symbolic domain. It's a program that we can then run on the structured representation. Everything on the left, these are neural networks that are basically lifting you out of the domain of the image or the question into a structured representation, symbolic domain, where you can actually do these operations. Now, the critical thing here is we're not just bolting these two things together. It's not the case that you can just bolt a CNN onto a symbolic program operation. But instead, what's happening is the whole system is jointly trained using reinforcement learning. So what that does is that allows the vision part to be better at extracting the symbols by virtue of having been part of this hybrid system. And it allows the language part of the network to be better at translating the question into an appropriate program, because when it does the right thing and executes the symbolic program, it gets the right answer. And then using reinforcement learning, you can train the system jointly. So this is a genuine hybrid. We're not just bolting things together. This is actually learning something different. Every part of the system is learning something different based on being part of the hybrid. And that's kind of the magic of it. And you take the vision part, you take the language part, You basically parse the scene into a set of entries, a symbolic representation of what the object is. You take the language part and then you parse it into a program, a series of operations, filter on red, and query the shape, and then you could join those two things together with symbolic reasoning, and then we do the whole thing with reinforcement learning. So this is basically just a restatement of what I just showed you. And then you'd execute the program, you get the answer. The answer's right, the answer's wrong. Now, when you do this, three magical things happen. Well, first of all, I mentioned earlier that this clever data set was created because it was kind of sort of unusually hard for neural networks to solve. Even though neural networks are amazing, it seemed like no matter how much data you throw at them, they would struggle to solve even this very simple task to a high level of accuracy. Now, it turns out when you do this neurosymbolic question answering approach, you can basically get effectively perfect performance. So just adding in a dash of symbolic processing allows you to achieve, basically, perfect performance on this task. So the clever task is no longer, it's basically a solved task, and we can move on to harder tasks. But another interesting thing happens, which is has to do with data efficiency. So you remember at the beginning of the talk, I said that one of the biggest challenges of deep learning, actually applying it in real world settings, is we rarely have so much data that we would need to train these systems. We need to work with small data, not big data. It turns out when you add, again, just a dash of symbolic processing to these systems, they're able to work with and train accuracy as high as deep learning, competitive deep learning systems, with just 1% of the amount of data that the other methods require. And if you allow the system 10% of the amount of data that the deep learning methods require, you can basically completely solve the task. So we're getting at somewhere between a 10 and 100-fold reduction in the amount of data you need to be able to use these systems. And just to unpack this plot, the number of training examples that you get is on the x-axis, the accuracy of the systems on the y-axis, and the blue is the neurosymbolic system. So it's just vastly more data efficient in addition to doing better at asymptotic performance. So and what's happening here is the neural networks, while they have to kind of learn the reasoning part, by memorizing basically lots of data, and like learning all those different corner cases, by just adding in a dash of compositionality that comes from the symbolic AI, we're able to achieve amazing results. And then the third advantage is, I mentioned that explainability and interpretability was a big problem for AI in real world settings. You get transparency and interpretability with these systems basically for free. And the reason is that the systems, by virtue of going through a symbolic choke point in the middle, basically show their work. So you can see the operations that the network and the combined hybrid system use to get the answer. And you can just ask, is it getting the right answer for the right reason? So you can say, did it go through the right steps? You can also interrogate, did it ground the systems appropriately, the symbols appropriately in the image? So like when it looked for metal things, did it actually correctly identify? You can actually trace back and find out if that was the case. And one of the things we found actually when we look at many state-of-the-art visual question answering systems, even when they get the right answer, oftentimes they're actually getting the right answer for the wrong reason. So several groups have found that in many visual question answering tasks, if you just look at the question, you can get the answer, because there's statistical biases in how the questions are formed and what the images look like. So this is a great case where we can actually understand why I got the right answer, or if got the right answer, we can kind of look in there and try and understand how we might be able to fix it. So these three properties really, we would argue, are kind of game changing for AI. Now, this is work we did back in 2018, but this is a research program in the lab. So going from, this paper in 2018 where, basically the properties of the objects, like color and the values of those properties, like red or blue, were predefined. This is a very predefined sort of domain-specific language we used for the program. But basically, this team has been on a warpath of each new conference getting a new, in this case, another spotlight, another oral paper in iClear, which is the next conference. In this case, something called the Neuro-Symbolic Concept Learner, which could learn new values, like we could learn a new color from context. And then they had, at the next NeurUps, they had something called the Neurosymbolic Meta-Concept Learner, which could learn relationships between concepts. And then the next iClear, extending this to dynamic scenes, being able to do counterfactual reasoning. And this is kind of an ongoing program of research. And what I want to kind of paint a picture for you in the kind of a vision is these systems are getting less and less predefined and more genuinely autonomous. So they're able to acquire more knowledge organically and process in a symbolic way, as we go. And just to give you a flavor, I don't have a ton of time, but to give you a little bit of a flavor of how these work, The neurosymbolic concept learner, for instance, is able to learn from context new symbols, like red. It can learn what red means even if it hasn't seen it before. And the way it does that is basically embedding the visual representation, in a vector space, and embedding the concepts, so that you would take an object one, in this case that was identified by the CNN, embed it in some general representation space, and then have a way of mapping it into a color space, and then mapping the other object. And then when you have a concept that you've learned, like red, you can then decide, you can reason about whether that applies to the different concepts that lives in a joint embedding space. And what this lets you do then is, if you encounter new symbols that you don't understand what they mean, you can now learn them and then ground them in that space and refine your understanding of those symbols. So it makes the system able to not only work with predefined symbolic knowledge, but actually to acquire new symbolic knowledge. The other piece I mentioned earlier about symbolic AI that's really powerful is that there's all these relationships between different kinds of knowledge. And the team produced a system called the Neuro-Symbolic Meta-Concept Learner in 2019 at NeurIPS, which included visual reasoning questions like before, but also these sort of meta-conceptual questions like, is red the same kind of concept as green, or is cube a synonym of block? And then you can imagine, even on regular images, are there superordinate, subordinates, or relationships? Is Laraday a hypernym of ivory gold, and so on and so forth. So I'm just going to skip through this a little bit quickly, just we don't get into it. But just suffice to say, you can learn these relationships autonomously, learn symbolic relationships between different kinds of knowledge, different kinds of symbols. I'm just going to skip through this. And then more recently, the team has now extended this to dynamic scenes. So Clever as a data set is already basically solved. So the team is now moving on to video. So you can answer, once you start having dynamic scenes, things get kind of interesting, because you can have different kinds of questions. Like you could watch a video of some objects interacting, and then you could ask a descriptive question like, what is the material of the last object to collide with the cyan cylinder? In this case, it's metal. So this requires you to describe a complex dynamic scene that you've seen. Also could be explanatory, like what is responsible for the collision between the rubber and the metal cylinder. So this is like a deeper level of understanding. You're actually explaining why something happened, rather than just simply identifying what happened. And then, interestingly, you can also do counterfactual questions, like, what would happen without the cyan cylinder? If the cyan cylinder weren't there, what would have happened? And this is even a more advanced form of reasoning, because it allows you to hypothesize about, answer questions about things you didn't see, you didn't experience. And these systems require you to build a dynamic model of the world, and then be able to symbolically reason about it. And this is work. This is a data set called Clever. This was introduced. This was a paper at ICLR this year. So that's kind of a whirlwind tour of kind of some of the initial work we've been doing in Neuro-Symbolic AI. But looking ahead, actually, when you look at kind of real world problems, these are toy problems that we've been working on so far. A lot of problems have this kind of quality to them in real enterprise settings. The real problems we're going to solve. Oftentimes they aren't kind of a map from what I have to what I need kind of prediction problems. They're more like little one-off puzzles. Like, you need to be able to answer, like, I want to know how many employees have over 10 years of experience and have moved location in the last year. Why do I want to know? It doesn't matter. I want to know at one time, and I'm never going to ask that question again. So it's not like you could train a system classifier to tell you that answer, or a arrestor to tell you that answer. It's like you need to be able to pull lots of different data sources, be able to reason about them to answer a question. Or, why might factory A do better than factory B? This requires lots of different information to pull together. Or why is our database down? Like, if you're running a database, you have an IT system and your database goes down, is that because you've been hacked by hackers? They've intruded your network and caused mayhem, or is it because somebody pushed bad code into production and you're DDoSing your own database? Those kinds of things, we solve those kind of problems all the time. I would even argue that 95% of the problems that we actually solve in our day-to-day life have more of that puzzle-solving quality to them, where you're not going to get millions of training examples of hackers hacking your network. It matters the very first time it happens. happens. Like, you need to be able to then look at the situation, understand it, reason about it, come up with a solution. And that has a very different framing than this sort of brute force deep learning model, but that's really what we're ultimately after. And to tackle these kinds of problems, we're actually doing a whole program of different kinds of research in neurosymbolic AI. Everything from neurosymbolic generative models, being able to have generative models that have symbolically interpretable latent space, safe ML and RL. So one of the reasons you might want symbolic AI mixed in is sometimes you want to be able to have verifiable safety constraints. Imagine a self-driving car. You'd like to symbolically express what's allowed and what's not allowed in terms of safety. How do you train a neural network in a way that respects those? Or neurosymbolic natural language understanding. How do you actually extract, knowledge and structures, like grammar trees, but also, like symbolic representations of the ideas that are conveyed by a piece of natural language. This is an area where we work. We also work in the area of neurosymbolic planning. So planning is another field of symbolic AI where you can use symbolic methods to search for ways to go from one state to another state in a verifiably correct way. We have work going on where we're mixing those ideas with neural network ideas to achieve better work in different domains and achieve better performance. We'll even have areas like neurosymbolic code optimization. Code is fundamentally symbolic, but you can use neural networks to manipulate those symbols in ways that allow, for instance, code to run faster. And then finally, we also have a lot of work going on in what we call machine common sense. And in fact, we're participating in a DARPA program. DARPA is the US Defense Department Advanced Research Projects Administration, where we're trying to have AI systems that have all of that common sense knowledge that we take for granted, but it's not really written down anywhere, about the different kinds of affordances that objects have when they interact with each other. With that, sorry, I got this going the wrong way. So with that, I'm gonna close and just leave some time for questions. I hope that I've left you with a little bit of a flavor of how these very powerful technologies like deep learning and symbolic AI can be combined in interesting and ultimately very valuable ways. And I think this is a research program that we're going to take in lots of different directions and achieve lots of different things. And we're particularly excited, to be working with our Brazil lab, who do quite a bit of work also in neurosymbolic AI, but particularly now that we have this new collaboration with University of Sao Paulo, we're very open to finding new ways to collaborate. So with that, I'll stop and thank you for your attention. And if you have any questions, please don't hesitate to ask. Thank you.
So first of all, thank you so much, David. I think it's a great talk. Our feed is full of questions, and I also thank everyone who is there. We'll see how many we can get through. But as I said, we're giving here the first talk of a seminar that the center will have, which we call Perspectives in AI, and it will be probably monthly. And I'm planning to ask everyone in the seminar the same question to start the debate. And the question is, what's the impact of 2020 in AI research? In sense, we are in a crazy year.
Yeah.
And also in the use of society. How the pandemic, all that's happening this year will affect.
That's a fantastic question. I think what we're seeing and what we're hearing from, we interact with many of IBM's clients. 2020 broke a lot of AI models. So there are a lot of predictive AI models that are out in the world, and the reason that the models broke, and this is actually important and fundamental, and this is something very close to our hearts in terms of our research program. Most of our AI methods we have today are fundamentally correlational. People talk about mining for patterns in the data, things like that. So they're finding relationships between data, but that's not really what we want. What we really want is models that are based on cause and effect. So for instance, if you built a model that was trying to predict like how much revenue am I going to get at a fancy grocery store? How many people are going to shop at my fancy grocery store? If I had data on how many people go to fancy restaurants, I could build a machine learning model that would predict from how many people are shopping at fancy restaurants, whether they're going to be shopping at fancy grocery stores, the nice grocery store with the special, good produce. Now, all of a sudden, COVID times, like your model's giving you exactly the wrong answer. Nobody's going to any restaurants. I don't know how it is in Brazil, but in the United States, nobody's going to restaurants, and our grocery store shopping has shot up. So these two variables that normally track together, all of a sudden now are anti-correlated. Or if you're trying to build models of the economy, the price of oil and the price of airline stocks, those are normally anti-correlated. If the price of oil goes down, that means it's cheaper to fly. That means airlines are going to make more profit. That means the airline stocks go up. No, both are down. And the reason is there's a latent confounding variable, which is demand for travel, which is hammering both of those. So the correlations we see actually aren't so deep. They're all at the surface level. And if we rely on AI systems, machine learning systems that fundamentally just find patterns and correlations between the data and don't understand why, don't understand the cause and the effect, those models are going to be incredibly fragile, and they're going to break when you have a covariate shift like we have with COVID-19. But the fact of the matter is, COVID-19 is really just showing us that we have a problem. We had the problem before, we just didn't know it. If you talk to anyone who's actually tried to deploy AI systems like this in practice, most of the people you talk to will be obsessed about model drift. Like, how do you deal with model drift? If they, either they try to deploy and they eventually fail because the models stop working, or they learn to be obsessed about model drift. And IBM, for instance, has all kinds of tools for helping you monitor drift and constantly sort of do model ops to kind of keep things going. But I think what we need to do, what's going to spur is a new activity in trying to build models that are fundamentally focused on causation. And there's a field of AI called causal inference, which many of you may know about. It's been around for a while, but I would argue that it's kind of coming into its own now, where you can do three things. One is that you can take observational data, and using the statistical properties of conditional independence testing, you can actually infer, in some cases, putative causal relationships. So you can know that this probably causes that, not the other way around. There's a whole subfield around understanding what experiments you might want to schedule to be able to do sort of A/B testing to figure out if you got the right directionality. And then the third piece is, if once you have a causal graph, and the models are fundamentally graphs, they're like nodes that are the variables and directed edges that are the relationships, then you can use that causal graph to make better decisions. And what that also lets you do is put in a priori knowledge about the causal structure. So, and this is important in all kinds of deceptive ways. So in the United States, in our state of Florida, the courts in Florida put into practice a machine learning system to decide whether or not inmates were likely to commit crimes again, to recommit crimes. And they decided they would use this to help decide whether to give parole, whether to let them out or keep them in jail. The idea was that this was going to be not racist, and this was going to be less biased than the human judges, because they were going to blind the system to race. They were not going to tell the system what race the people are. And lo and behold, the system dramatically more likely to say that a black person is going to reoffend than to say a white person is going to reoffend. And the reason for that is that your race, you can't get rid of the race. The race is tied up in all the correlations and the demographics of the data being fed to this model. So you're basically just laundering the bias. You're pretending like the bias is there because you're having an algorithm commit the bias. And it turns out the solution to this problem, this is being driven by a group at MIT, not the group that we work with, but we definitely follow their work, where they're advocating that the solution is causal inference. So if you have a causal model of all the variables and how they interact to cause recommission of crimes, you can say a priori, I know there is no link. I'm going to cut the link between race and recidivism, or recommitting crimes, and then tell me now to make the decision with that link gone. So if I know a link isn't there, I can erase it. If I know a link is there, I can put it in. I know a link has a particular direction, I can just put that a priori knowledge in. And this is a very powerful toolkit. I think it's going to actually change how we do AI and machine learning, data science in the future. I think we're going to have a new toolkit. And this is actually very close to our hearts in the work we're doing in Neuro-Symbolic AI. I mentioned that we're doing counterfactual reasoning in some cases, and that's very much a hallmark of building causal models and then being able to run those causal models in scenarios other than the ones you observed. So I think that's going to be a huge takeaway from COVID. The other way that it's changing, of course, the field is we're doing all these things remote. That's a double-edged sword. I would love to be in Sao Paulo right now, visiting you in person. It's a lovely city. I love Brazil, but unfortunately we have to do this remotely. On the other hand, like the jet lag is much better this way. Like the wear and tear, from traveling. I'm not traveling to Asia every 2 weeks and things like that. So there's much more participation. So I think we're going to see some democratization of AI as a field, which is great. But obviously, we have a slightly lower, lower touch sort of way of doing it.
Oh, great. So I guess I have one more way to label 2020, saying is the year that we broke all correlations. That's a great way to define it. I love that. So we have a question that a lot of people, they posted that they want to ask a question is by Fabio Cosma, who's the co-director of the center.
Mm-hmm.
And he said, and the question is, as a neuroscientist, mm-hmm. do you see this idea of dividing perception and reason, as Tenenbaum did, mm-hmm. as an engineering solution or something that's similar to human intelligence?
Yeah, that's a great question. It's interesting. So I really enjoy working with Josh because we both kind of have this dual role where we've Josh is a cognitive scientist at heart, but he also was the person. He often is the person who publishes the most papers at NeurIPS, like at an AI conference. And I've always run a joint program, a joint lab where I've done half neuroscience, and half appointment in computer science, half appointment in neuroscience. So there's some kind of interplay there. Like clearly our brains are implemented with neuron-like machinery, right? Like we have, probably more like deep learning than they are like symbolic processing. But on the other hand, I'm personally kind of agnostic about, could we coerce neural networks into doing something like symbolic reasoning? I think we probably could, but as an engineering solution, there's no requirement to do that. And there's many advantages. For instance, I kind of alluded to the fact that there's you can do formal verification for safety if you have a symbolic system. So that's a case where, by virtue of doing it in a genuinely symbolic mode, rather than using neural networks, the way our own brain does, perhaps, to do the symbolic reasoning, you can get some advantages that are superhuman. Like we can have formal guarantees on symbolic operations that we can't have with our own brains. I do think, though, that Josh's work, Josh's sort of orientation, my orientation in the world, is that the symbolic manipulation is very human. Like this is something that we absolutely do. We absolutely manipulate symbols, and there's all kinds of reasons. Not just, we don't just need to ape whatever the brain does to get the answer, but there's good reasons to reduce things down to symbols, right? Like sample efficiency is a huge problem, and of course, if you need to be fitting huge numbers of parameters, you need to have lots of training data. And that's one of the big problems we have here. Whereas we seem to naturally reduce the world to a small number of objects, understand their interactions in smaller groups, and that's really fundamental to our ability to do these high-level tasks. So I would say we're continually inspired by the brain, by neuroscience. We're constantly using that as a guiding star. We don't necessarily feel beholden though to it. So like we can do engineering solutions. We believe that a lot of this is actually quite close to how the brain does it, but we don't need to be limited by like slavishly copying how the brain does it. And that's sort of just our own sort of orientation about how we think about these things. But I think that interplay is really interesting and really exciting.
Great. Now, I'm not sure if you know, but I was a colleague of Joshua at MIT. He was at the Media Lab at the same time. So
okay, great.
He also had really smart at that time. So. I wonder if I can put one more question here. I think we are getting to the top of the hour we have here. There's this question from Michelle saying, how do you see the potential of the current transferring learning techniques to push our AI systems from the narrow to broad? Is this part of the path?
Yeah. So clearly we need to be able to do better domain transfer. Like that's a huge barrier. I mean, we're at a level now where if you're not, famously it was shown that you could train an image recognition system on one data set. You got to train it to identify which data set you're looking at. So the data sets have subtle distributions and subtle differences in the distributions, and we tend to overfit to those distributions. So just all kinds of problems just even at the level of are you getting the right answer about the perception problem, for instance. And this is why domain transfer is still a very hot area. We publish a lot of papers in the area. We have a few going out to CVPR soon about doing transfer learning and domain transfer. I think really what we need to get to, though, like the solution to all of this is really much more about actually extracting the structure of the world. Like, I think the surest way to do domain transfer is not to come up with hacks. So there are useful hacks to get kind of like, how do I take my classifier and adapt it to a new domain with limited amounts of data? Those kinds of things are going to be tactically interesting and important for a while. But what we really need to get to is like actually understanding the latent causes of an image. Like, what are the surfaces and the edges and the lighting that produce this image? And that having that deeper understanding of extracting the structure of the world is helpful, because then even if we don't have labels, like we can reason about objects that we don't have labels for. We can do things like, how heavy is this object likely to be, or how would you need to shape your hand to pick up this object? You don't need to have extensive training with that object. You can do that with a completely brand new object. So the question of domain shift and transfer learning, it feels a little bit like, sometimes like if your goal is to go to the moon, it is the case that if I climb a tree, I am getting closer to the moon, but I'm not getting closer than the top of that tree, right? It's like, if my only goal is to get closer to the tree, like, yes, this will work for a little while, but then I have no path going forward. And I feel sometimes like some of these, sort of more classical domain transfer problems feel a little bit like, okay, well, this is going to help in the near term, but what we really need to do to get to the real answer is be able to like flexibly, extract structure, so that, to avoid problems like, if I have a dog, like a 10-foot metal dog with pink polka dots, like a sculpture or something, I can reason about that being a dog, even though I've never seen one of those before, because I understand the properties of what make a dog a dog. That's the kind of robust transfer that I think we need to be focusing on. And it's true that the other kind of domain things are going to be important in the near term, but I think that's ultimately the solution to these problems, is really understand the structure and what are the sort of more symbolic properties that make these things what they are.
Well, we had a lot of great questions, but we have to end here. First of all, I'd like to thank you again for the talk and all the great ideas you shared with us. People that ask the questions we may send to you, so you get some feedback.
Sure. Thank you.
And as I said, this is the first talk of the seminar of the perspectives of AI. It's a seminar by the Center for Artificial Intelligence that we hope we can continue hold them with the society that hosts BRACIS. And again, unfortunately, one of the things about virtual talks, you cannot applaud you, but I know in the name of the audience, I'm going to do that. Thank you so much.
It was a pleasure. Thanks for inviting me.
Thank you again, and sorry for the delay, but it was great to have you here. Absolutely great. Thank you, everyone. Thank you for the audience. Thank you for the great questions. The conference continues.
Great. Thank you.
Thank you.